So let's look at section 5.2. We're just going to do more work with exponents and scientific notation. So here are three more rules. I just updated the last rule to say power of a quotient rule. You may have a worksheet that just says quotient rule, but this distinguishes the quotient rule we used in 5.1 from this one. So we have these three, and they're really important that you learn. And let's look at the power rule. So the power rule says, given some base A raised to some power n, now if that itself becomes a new base for another power m, or exponent m, then the result is you just take the base and multiply n times m. So let's give an example and a justification for that. A really simple one. We will do 2 to the third. So the base here is 2 and the exponent's third is 3. And I'm going to turn that into another base raised to another exponent. So let's look at what's in parentheses first. What's in parentheses is 2 times 2 times 2. And that becomes a new base that is raised to the second power. So by definition of raising to powers, my base is 2 times 2 times 2. And I'm multiplying it by itself twice, and I get a total of 6 2's, and 6 is equal to 2 times 3. So just using our regular rule, the power rule, we would immediately write this is equal to 2 to the 3 times 2, not adding anymore, which is equal to 2 to the 6. So when do you add and when do you multiply? Here is the difference. I'm going to go back to my x as a base. X to the n times x to the m. Two different occurrences of the bases. They're multiplied. So we get x to the n plus m. See how that looks different? Versus x raised to the n, which becomes a new base for another power raise. That's x to the n times m. So along those same lines, we have another one. And these are really the only two new ones, and the others are natural extensions of it, especially power of the quotient rule. This is called power of the product rule. Suppose I have A, my base is a product. My base is A times B. So that is my base. So make sure you understand what your base is. And I'm raising that product to the nth power. Well, the rule says that's equal to A to the n times b to the n. So let's do this in an example. Let's do 2 times 3 squared. Well, that's by this notation, or this rule, 2 squared times 3 squared, which is 4 times 9, which is 36. So here's my base. My base is a product. In this case, 2 would be A, and 3 would be B, and I'm squaring it. And this is just an application of the rule, where in this case n is equal to 2. So let's justify that. Well, let's do 2 times 3 squared. Well, that's 2 times 3 times 2 times 3, because my base is multiplied by itself twice. So using the property of commutation of multiplication, that's the same as 2 times 2 times 3, just arranging factors. And then by definition of exponents, that's 2 squared times 3 squared. So that's the justification for the second. And the third is, if I have a quotient, a divided by b, then it's just a to the n divided by b to the n. And literally this rule, of course, we can't be dividing by 0. So this rule is just a special case of the power rule, because when I say let a be a base, that means a is a real number. And clearly fractions like c over d are real numbers. So c over d to the third power is c divided by d, c divided by d, c divided by d. That's supposed to be a d, which is c times c times c, c cubed, d times d times d, d cubed. So let's just do some exercises. I don't care that you know the names of the rules or not. I always get them. There's too many different names. I just know what they do. So let's do 1a. So x to the 5th raised to the 7th power. So again, just note that my base is itself something raised to a power. So this is telling you to use the power rule. So that's just equal to x to the 5 times 7, which is equal to x to the 35. So here we have 2 squared times 3. So again, my base here is something raised to an exponent. So I go ahead and use my power rule. And that's equal to 2 raised to the 2 times 3, which is equal to 2 to the 6th. Let's look at number 1c. 5 to the minus 1 squared. It works. It doesn't matter that that's a negative. That's equal to 5 raised to the minus 1 times 2, which is equal to 5 to the minus 2. And if they want positive exponents, you would put the 5 to the minus 2 below the, make it go across the division sign so that that 2 becomes a plus. Again, we don't write the plus, but I put it there just so you can see that the sign changed from negative to non-negative. In the sense that it doesn't have a minus sign on it. 1d, y to the minus 3 to the minus 4. Again, it's an x something with an exponent raised to another exponent. So that's y to the minus 3 times minus 4, which is equal to y to the 12. Because minus 3 times minus 4 is 12. More problems. You just do a lot of these until you get the hang of it. And as far as visually looking at them in my math lab, they can be really scary at first sight, but you just get your system down and you'll be fine. So this is 5x squared, and all of that's cubed. So I'm going to actually combine two different rules here. The first is going to be a power of the product rule, because notice my base is a product. So that means that's 5 cubed times x squared cubed. So I'm assuming you've got your rules there in front of you. Take a look at the power of a product rule, a times b raised to the nth power. Now we just simplify. 5 to the third power is 5 times 5, which is 25, times 5, that's 125. And now I use just the plain power rule. X squared to the third is x to the 2 times 3. So the final answer is 125 x to the 6th. So here we're going to use the power of a quotient rule, 2/3 cubed. Well, we just apply the exponent to the numerator and to the denominator. And we can simplify that. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. So here they're mixing things up again. We're going to use several rules at once. 3p to the 4th over q to the 5th. So if you remember PEMDAS, it tells us to do exponentiation first. Parentheses first, then exponentiation. However, in this particular case, there's nothing you can do inside the parentheses to simplify anything. There's no simplification possible for 3p to the 4th divided by q to the 5th. So nothing to be done here. So we're going to move to exponentiation. So what I'm going to use is the quotient rule. And I'm going to have, since the numerator is a product, 3 times p to the 4th, I'm going to put it in parentheses and square it. And then I'm going to put the bottom in parentheses and square it. Now for the top, simplify. This is going to be power of a product rule, because 3p to the 4th is a product. The first factor is 3, and the second factor is p to the 4th. So this is 3 squared times p to the 4th squared. And this is over. I can immediately use the power rule for the denominator. That's q to the 5 times 2. So let's go ahead and simplify some more. That's equal to 3 squared is 3 times 3, that's 9. P to the 4th squared is p to the 4 times 2, which is p to the 8th. And then I have q to the 5 times 2, which is 10. So the final answer, let me write it, so I don't know if you can see the 8 there really good. It's 9 times p to the 8th, q to the 10th. And our last one is 2D. We have x to the minus 5, y squared, z to the minus 1, and all of this is raised to the second power. So we're using basically the power of a product rule, because the base is a product, right? It's x to the minus 5th, that's one factor, y squared is another factor, and z to the minus 1 is another factor. So I'm going to break it up. X to the minus 5 squared times y squared, which is squared, times z to the minus 1, which is squared. Now I'm going to use the power rule. So that's 8 times minus 5 times 2 is minus 10 times y squared squared is y to the 2 times 2, which is 4. Z to the minus 1 power squared is z to the minus 1 times 2, which is minus 2. They want you to write all of this with positive exponents. So the only factor up here with a positive exponent is y to the 4th. So I'm going to leave it at the top of the division line and then put x to the 10th times z to the 2nd across the division line so that they become positive. So just so you understand, x to the minus 10th times y to the 4th times z to the minus 2. It doesn't have a written division line, but I can always add 1 by saying it's divided by 1. And now, of course, when I move a factor down below the division line, it's replaced by a factor of 1. It becomes x to the 10th. And z, again, it's replaced by a factor of 1, and it becomes z squared. So these disappear in the sense that they've been moved down here, and they're replaced by 1. So 1 times y to the 4th times 1 is just y to the 4th, and x to the 10th times 1 times z squared is just x to the 10th times z squared. And customarily we don't write the dot in between there. I'm just writing it now just to emphasize. You can feel free to write the dot if you want to. My math lab might not like it. I'm indifferent. So here is a summary rule. This is a great reference sheet of all of our exponent rules. So what I gave you, or that little bitty page that I referenced in the last video, is something you can use and keep, that you will be using later on in this semester. You'll be using all of those rules, and also for college algebra. So we're going to be, everything's in play now. Everything is play. And notice what it says. If a and b are real numbers, and m and n are any integers, that can be 0. An integer is a positive or negative whole number, or 0. So these can be the negative whole numbers or the positive whole numbers or 0. The only restriction is that the base cannot be equal to 0, and down here the base on the denominator can't be equal to 0. But for the most part we can ignore that for right now. So let's go ahead and do example A, B, C, and D. I'm going to challenge you to get the most really out of this lecture, and there's a lot of them. Chapter 5 is a pretty heavy hit. That's the reason I'm posting these early for at least my fall 2020 class. Other students who see this in the future, it probably won't apply the posting early. So we have 2x to the 0th power, y to the minus 3 to the minus 2. So let's use PEMDAS and simplify what's in parentheses. And we can simplify what's in parentheses because x to the 0th is 1. So that disappears. So that's 2y to the minus 3. When I say it disappears, but it doesn't really disappear, it changes into 1. But 1 is the multiplicative identity. Any number times 1 is just that number, so it doesn't change anything. So we just leave it out. And all of this is raised to the minus 2. So now the only thing we can do now is we've used the parentheses up, is we can take care of the exponents. So I'm going to have to use the power of a product rule here, because notice that my base is a product, 2 times y. 2 is one factor, y to the minus third is the other. So this is 2 to the minus 2 power y to the minus 3 times minus 2 power. Let's use these parentheses rather than a dot. So let's go ahead and simplify. So 2 to the minus 2, I'm going to drive that down underneath the division line so it will become positive. Y to the minus 3 times minus 2 is y to the 6th. So the only thing remaining for me to do is, I don't know what y is, so I cannot tell you a value of y to the 6th. This is a variable term, but I can tell you the value of 2 squared. That's 2 times 2. So it's y to the 6th divided by 4. And so let's do 3b. So here I have x to the minus 5 over x to the minus 2 raised to the minus 3. So to be quite honest with you, there isn't, the PEMDAS rule is kind of loose here. There isn't any real thing that we can do to simplify. Well, there is, of course. What we want to do is, eventually we want all positive exponents. So notice right here, both of my exponents are negative. So what I do is I move the one whose absolute value is the greatest across the division line. In that case, that's x to the minus 5. So that's x to the minus 2 stays as it is, and then I have x to the minus 5. When it's moved across the division line, becomes positive. I can't forget that all of this is raised to the minus third. So again, simplifying what's in parentheses, x to the minus 2 times x to the 5, that's just the plain old product rule. That's x to the minus 2 plus 5, which is x to the third. And I'm raising all of this to the minus 3. So now I'm literally going to go ahead and use the quotient rule. And that's 1 to the minus 3 over x cubed to the minus 3. Now here is a theorem. Let me help you out. Theorem. I don't think I have it in the notes. I don't think I added it. It's almost obvious. 1 raised to the n is equal to 1 for any value of n. Positive, negative, or 0. So that allows me to immediately simplify. It's an easy theorem to remember. 1 raised to any power is just 1. So the top is 1, and the bottom is x to the 3 to the minus 3. So bringing it up here, that's 1 over x. 3 times minus 3 is x to the 9. But we want this to be all positive exponents. So we're going to move x to the 9 at the top, and we're going to do 1 over x to the 9. And we're done. Let's do number C. C, we have 2/7 raised to the minus 2. Again, using PEMDAS, there's nothing I can do to reduce this fraction. So I immediately have to use the power of a quotient rule. And my next step is going to move the denominator across the division line to the numerator, and the numerator across the division line to the denominator, so I get positive exponents. 7 squared is 7 times 7, which is 49. And 2 squared is 2 times 2, which is 49 fourths. Let's go ahead and do number D. Yeah, it looks really hairy. But again, we'll simplify what's in parentheses first. You don't have to. There's other ways to do it. But by simplifying what's in parentheses first, we're being true to PEMDAS, orders of operation, and we're applying them. Okay. So let's do the simplification. So really what we want in the simplification is that, oh, there is no power. So literally I don't even need those parentheses. It's not raised to any power. And it could be a typo, maybe in the book it's raised to a power, but I don't know. We're just going to go with it as it is. So here's my division line. So let's take them element at a time. So 5 to the minus 2 crosses the division line and becomes 5 squared. Now let's look at the x terms. So I want the x terms to be positive. So if I move the x squared up, I'm going to have x to the minus 3 minus 2, it'll be negative. So I'm going to move x to the minus 3 down below, and that exponent becomes positive. Now here, I have y to the 11th, y to the minus 5th. If I were to move y to the 11 down below, the 11 would become negative. And I don't want that because I want positive exponents. So I want to bring y to the minus 5th, or y to the minus 5th, to the top. Now it's all just a matter of simplification. Y to the 11th times y to the 5th, same basis, side by side, multiplication, we add. The exponents are added. 11 plus 5 is 16. 5 squared is 25, and x squared times x to the third, I add the exponents. 2 plus 3 is 5. Okay, so not so bad. It looks pretty hairy, but it's not so bad. So more, just more. You have to do a lot of these until you get really good. And some of you have a natural knack at it. So this is number 4a. 5a to the 4th times b divided by a to the minus 8 times c. All of this now is raised to the minus 3rd. So again, we're going to use PEMDAS. And we're going to work on simplifying what's in parentheses. Because it's parentheses first, exponentiation second. So the only thing really that we can simplify here is concentrating on a to the 4th and a to the minus 8th. Now, this is the aggravation of it. What I'm going to do right now is going to be undone by this exponent right here, but we're literally just following the algorithm of PEMDAS, which doesn't necessarily mean it's the fastest route to the answer. But I'm going to go ahead and move the a to the 8th in the top, leaving the c all by itself down below. So this is going to be equal to, again, just simplifying the numerator. 5a, so this is just the plain old product rule. 4 plus 8 is 12. And there I have multiplied by my b, then my c. Now, if you see what's going to happen, I'm going to use the power of a quotient rule. So notice, be careful. I'm going to be wanting to put this in parentheses. It's going to be 5a to the 12th b raised to the minus 3 over c raised to the minus 3. Now let's get rid of the negative exponents. I mean, c to the minus 3 comes up, becomes c cubed, and then 5a to the 12th b to the 3rd stays on the bottom. And I'm almost done. All I have to do is simplify using the power of a product rule. So this is a product. Here's one factor, a to the 12th is another, b is another. So this is 5 to the 3rd. A to the 12th itself is raised to a 3rd, and b is raised to the 3rd. So we're almost there. So that's going to give me c to the 3rd. 5 cubed is 5 times 5, which is 25 times 5 is 125. Now a to the 12th to the 3rd, that's a to the 12 times 3, and b to the 3rd remains the same, no simplification there. And finally, this is c cubed over 125. A 12 times 3 is 36 b cubed. And there is no further simplification that we can do for that particular problem. And finally, one last big one. I'll write it down here. And again, we'll do this systemically. We will simplify each factors as much as we can first, and then we'll multiply them together. And there will be one like this on the exam, I'm quite sure of it. Just one though. 2x to the 4th over 5y to the minus 2. It's raised to the 3rd power. And I'm multiplying it by x to the minus 4th over 10y to the minus 2. And it's going to be multiplied by minus 1. So now that we have it here, what I'm going to do is I'm going to simplify both of them. Again, we're going to work on what's in parentheses first. In the simplification we have is we're going to make all of the exponents positive. You should be okay with what I just wrote right there. And the same over here. We're going to make all of the exponents positive. That means y to the minus 2 raises up across the division line, becomes y squared. And then I have 10x to the 4th. Now, what we need to do is apply our exponent, the quotient rule. So the quotient rule requires that I write the numerator, the product of a quotient rule, in parentheses and cube it. And then 5, I don't have to put it in parentheses, it's the only thing in the denominator, and it gets cubed. And remember, this is being multiplied. I'm multiplying these two factors. So y squared is raised to the minus 1, and 10x to the 4th is raised to the minus 1. So let's go up here and continue on. So let's go ahead and let's simplify the numerator here using the power of a product rule. So this is 2 to the 3rd. So this has three factors, 2, x to the fourth y squared, and they all have to be raised to the third power. Notice the use of parentheses here. And then 5 to the third is 125. We've done that several times. And over here, I'm just going to go ahead and use here y squared to the minus 1 is y to the minus 2, because 2 times minus 1 is minus 2. Here, this is again the power of a product rule. 10 to the minus 1 times x to the fourth to the minus 1. So let's simplify again. 2 cubed is 8. X to the fourth to the third power is x times 4 times 3, which is 12. Y squared to the third power is y to the 2 times 6, so y to the 6 over 125. Over here, what I'm going to do is I'm going to bring the only thing to simplify right here, and if you will indulge me, down here, x to the fourth to the minus 1 is equal to x to the minus fourth. So I'm going to go ahead and rewrite this, because I'm getting tired of writing so many steps, as x to the minus fourth. So I'm going to exchange places. I'm going to move the negatives in the numerator up so I can get rid of the negative exponents. When I said negative, I mean negative exponents. And then y squared at the bottom. So here is the last step. So to multiply two fractions is just to multiply every term. So what we do is we collect like terms. So 8 times 10 . Then let's collect the x terms. X to the 12th times x to the 4th. Then there's only one y term, that's y to the 6th. You can go ahead and put it in parentheses if you want. And then 125 y squared. So 8 times 10 is 80. X to the 12th times x to the 4th is x to the 12 plus 4, which is 16. Then I have y to the 6th, all over 125 y squared. We're not quite there yet. We still have to reduce this fraction. I can divide the numerator and the denominator by 5. 80 divided by 5 is 16, and 125 divided by 5 is 25. X to the 16 is the same, but I'm going to move this up here because 6 is larger in absolute value than 2. That gives me y to the 6th times y to the minus 2. So all of this is going to result into 16. 25 is the only thing in the denominator. X to the 16th. And 6 minus 2 is y to the 4th. And just being really, really careful, we got to the final answer. So, study. I'm going to take just a really short break here, not an actual break from talking. I want to explain why when we say x to the second power, we often say x squared. And I may have showed you this before. And x to the third power we say is x cubed. I teach so many classes I can't remember if I've got this down or not. Well, it has to do with the area of squares. So a square is a rectangle when all of the sides are equal. So if this side measures x and this side measures x, then when I fill in, I'm connecting these here. So when I fill in the space here, I get the area. And this area right here is the product, it's the area of a square, and it's equal to x times x, which is x squared. On the other hand, when we're talking about cubes, we're no longer talking about two-dimensional objects, but three-dimensional objects. You can imagine an aquarium if you want. So this is the best I can do freehanding. So that's a cube. And you can imagine its volume is determined by how much water if it's an aquarium. So notice there's three dimensions here. There's only two dimensions here. This is a two-dimensional object. This is a three-dimensional object. It has length of x, width of x, and height of x. So its volume, which I have no idea if this will work or not, we'll see. Volume is like filling up everything in an aquarium of that side. Its volume is x to the third, x times x times x, and that's the reason we say x cubed, because of the geometric figure of a cube, and that's the reason we say x squared, because of the geometric figure of the square. Those are concepts. The Greeks, absolutely. For the Greeks, number was equivalent to area, not length, but area. And that terminology comes to us all the way from classical times. So computing with scientific notation. So this is really kind of nifty here. This is a great application of what we've been doing, and a great simplification. So we have two numbers in scientific notation. This is 5a. So the first number is 8.1 times 10 to the 5th. And this is 5 times 10 to the minus 7. And for reasons having to do with the engineers and the scientists, we use the symbol of x to mean times. But let's look at it this way. Suppose this was, let me make this a little bit bigger. Suppose this was x times b to the 5th, 1x, a times b to the 5th, times c times b to the minus 7th. Well, we could write this as x times b to the 5th, a times b to the 5th. We could write it using the x symbol, and it becomes that way. So we're used to this notation, and this just looks weird because we've introduced usually an unwritten symbol here for times, which is the X symbol. But notice how easy this one is to solve. Of course, we don't know what A and B is, so we just collect those two terms together, and then not A and B, we don't know what A and C is. We don't know what A, C, or B is, so we multiply A times C, and that's B to the 5th times B to the minus 7th. So it's AC B to the minus 2, which could be written as AC times B to the minus 2. So that's exactly the technique that's going to allow us to solve this problem. So remembering this is just times, what we do is I just take the D values in each of the numbers written in scientific notation, and then I multiply it times 10 to the 5th times 10 to the minus 7. Well, 81 times 0.5 is 40.5. And the bases are the same. The base is 10. So I just add the exponents. So it's 10 to the minus 2. But does anyone see a problem? This is absolutely numerically correct, but it's not in scientific notation. Because scientific notation is in the form D times 10 to some power m, where D is greater than or equal to 1, but less than 10. 40.5 is greater than 10. So what I have to do here is I have to transform my 40.5 into, by moving the decimal one place over. So what happened? 40.05 just became a smaller number. So that means I have to multiply it by a larger number. So I add 1 to the exponent. So minus 2 plus 1. So I get 4.05 times 10 to the minus 1. So when you move to the left, you add to the exponent. If you had to move to the right, in other words, to get to your value of D, then you would subtract. And why are you subtracting? Just the number of places that you had to move. And let's do one other. So again, this is it looks much harder than it really is. So I have 1.2 times 10 to the 4th divided by 3 times 10 to the minus 2. Well, that's going to be equal to 1.2 divided by 3 times 10 to the 4th over 10 to the minus 2. Now 1.2 divided by 3. Well, that's the same thing as, let me do it this way. I've been avoiding this. 1.2 divided by 3. I want to get rid of that decimal. So what do I do to get rid of the decimal? I just move it to the right one place. That's the same thing as multiplying the quantity by 1 disguised in the form of 10 over 10. So 1.2 times 10 is 12, and 3 times 10 is 30. So you can already see that this is going to result in a number which is less than 1. Why? The numerator is less than the denominator. But it's probably easier for you to divide 12 by 30. Well, it won't go. So an add is 0. Now 30 will go into 120 4 times. I'm done. So this is equal to 0.4 times 10 to the 4th divided by 10 to the minus 2. That's 4 plus 2 because I can bring the 10 to the minus 2 up. So that's 10 to the 4th times 10 squared. So the answer is not quite in the form we want, but we're close. Again, we have the problem with the d value. The d value is this value right here. And 0.4 is less than 1. So what do I have to do is I have to move it to the right one place. So moving to the right, what do? Go back over and look at my notes. Moving to the right means we subtract. Why is that? I just increased the value of the number, so I have to decrease the value of the exponent. I moved it to the right by 1, so I subtract 1 from 6. I get 4.0, if you want to do it that way, times 10 to the 5th. Actually, just 4 times 10 to the 5th is fine. If you go on and you take science classes, you'll learn concepts such as significant digits, and depending on the significant digit accuracy of this problem would depend on how many decimal places, whether you put 4, 4.0, 4.00, etc. But this is good enough for us right now. I believe that's it for, so that's it for exponents and scientific notation.